So here is a sentence which is Max Verstappen and Valtteri Bottas fought an epic battle. If this is a sentence, how do we represent this as an input to the overall neural network that we might have? Okay, so one way to think about this is essentially a sequence of words. So Max is the first word, Verstappen is the second word, and is the third, and so on, right? So we can sequence them in this sequence that we have, right? So from x1 to x9 is going to be essentially the different sequence that will represent this word. So this will be the input that we need to find, and the key thing is it's important to have this in mind, is the Max is the first word and battle is the last word, and how those words are connected is important in this overall architecture or overall problem, because different combination of words occur semantically very close to each other depending upon the context that we might have. Okay. So the overall length of this sequence is 9, so that's why we'll call this as Tx equal to 9 for this problem. Okay. Now the output, and let's say if this is like a sort of a name identification problem, we are essentially interested in basically labeling the words which represent a name, and that might be an application. And this is an application where basically you have a web crawler crawl a lot of sentences and automatically grab the name of the people and probably their contact information. And if you want to build that kind of app, you need to have a machine learning model that does that. And in that, you might be interested in basically taking the sentence and figuring out the words which are names, right? So if that's the case, this is the problem that we are solving. And for that, the representation for input is going to be this, where the number of length is 9, and the output is essentially going to be this, where the word Max and Verstappen is 1 and 1, because these are related to the names. Whereas anything that is not in this sequence of word a name, which is and, fought, and epic battle, they are 0, 0, 0, 0, and 0, because they are not named. Similarly, Valtteri Bottas, which is 1 and 1, is essentially what we want to represent, because out of this 9 words, 4 of them are essentially related to names, and that's what we want to find out and label, right? So this will be our Y labels, which is 1, 1, 0, 1, 0, 0, 0, 0 for this data set. Now, one of the things that probably for sure, that any problem that we solve, especially using machine learning or any architecture, we need to have proper representation. And what we mean by representation is somehow you have to take the problem and you have to take the data and you have to convert that into a set of numbers which could be stacked together to create a vector, or it could be stacked together to create a matrix. Now you can see, at least for this problem, right, how we can create a vector for an output. But let's talk about the X, how we can represent this as a vector, or how can we represent this as a matrix, because right now it is a letter, right? So this is basically not in the form of numbers that any algorithm can take and process. So what we need to do is we need to take this X and we need to convert that into a vector. So let's see how the representation for X is done, especially for the recurrent neural network, if the problem is natural language processing. And I want to stop here and also emphasize that, especially if you have any natural language processing problem where we have a sequence of words or sequence of sentences and so on, RNN becomes even more important. It's very similar to what you have seen for CNN, where the images are input, then CNN is the very good architecture. Similarly, if your problem somehow involves any sequence of words, sentences, and so on, in that setting, RNN is a very, very good model. So let's talk about how to represent a sequence of words and what is typically used to represent. Y represented is clear, but let's talk about what the X is represented. Okay, so again, here in this case, the number of output that we have, Y, is also Ty. In this case, we have the output is equal to input, but that might not be true in many cases, and all the RNN architecture are flexible to handle the various aspects of this being Tx being different than Ty in many settings that we have. Okay, so again, what we want to do is our main focus here is to represent X. We understand how to represent Y, but let's focus on representing X, because if we cannot represent it, we cannot process it, right? So typically what is done in order to represent a set of words in a sequence is we use what is known as one-hot encoding. And what I mean by that is, let's say, for a given application problem, you will first of all define a dictionary. And that dictionary might contain all the words that you may be using in your machine learning or RNN development or for your application domain. And let's say you have a 10,000 word of dictionary, right? That goes that is typically used as an input or used as an output. That will essentially constitute, the overall dictionary. In the dictionary, all the words, and then there is one specific word which is known as UNK or as unknown, which basically specifies, like, there might be, you have created a dictionary, and when you're testing something, right, you might fall into a situation where you might have a word which is not in the dictionary that you have used to train your model. So in order to take into account of that aspect and in order to handle that situation, typically all the last element of that dictionary will contain UNK or unknown, and that would be anything that is not recognized will fall into that broader category of unknowns that we have there. So again, you begin with this dictionary, and let's say, at least for what we are building here, name recognition algorithm, then let's say we have 10,000 word dictionary that we have stored. So we can take, the words in this sequence and we can organize them. We can sort them in, basically using the dictionary item where the first letter and the second letter and the sequence that is ordering, that will help us in sorting from and maybe to, the last word that we are interested in. And the first location, first word in this dictionary is and, so that's the first location. Maybe max is located at 5877. That's the location that we have. So essentially, we now have a vector that allows us to represent 10,000 words in the dictionary. Okay. From there, what we do is we start picking the location of a specific word in the dictionary, and that helps us in representing all this x1, x2, x3, x4. So let's see how this works. So now let's see if you want to represent max, and max is at 5877 location in the overall dictionary that we have. So what one-hot vector does is it will make everything 0 except the 5877, which is the location of the max in the overall initial dictionary that we have. And this is why we call one-hot, because only one is switched on or becomes hot for a specific word among all the words that you have in the overall dictionary that we have. So this becomes, right, representation for max. So this is essentially a 10,000 element vector where everything is 0 except the element that is at 5877 location. Okay. Similarly, we will have Verstappen that will be represented, right? For this, the vector that we will use is going to be one-hot, or the one is going to be switched on at the location 7305, and everything else is going to be equal to 0. Similarly, we can represent and. Maybe for and only the 400 element is on and everything else is 0. And same ways we can represent all the remaining probably words. For and is probably the first element, so we will have the first one on, and everything else is going to be equal to 0. So this now 9 sequence of this 10,000 dimensional vectors are going to become an input to the overall training model that we have. Now, so this is one-hot encoding, which is one way to represent a set of words, which is typically a natural language processing element that is there. But now recently there has been other development in the representation aspect, and now typically you do not use one-hot vector, you use what is known as word-to-vec, or the more recent one is called BERT, B-E-R-T, and that is a representation which has been trained so millions and millions of data set. And what it does is when you provide that representation of word, it will automatically give you an output of a vector which is in some latent space and which is very, very smaller compared to this 10,000 space that we have. Maybe only 300 elements that will be used to describe that vector, but that vector could be used to represent the words that you have. So in any case, whether you are using one-hot or whether you are using word-to-vec or whether you are using BERT, you will essentially get a vector that will represent a given word that we have. So what we have done? So we have done now is we have our output, which is represented by a vector, because this is only one element. So one by one element could be used to represent this, and in X is also represented by a set of vectors. Now, if that is the case, what we can do is we can now use this input and output mapping, and you can try different architecture that might be there. So let's see what we can do with this input and output in classical deep neural network, and why we need some aspects that is very, very important and pertinent to the recurrent neural network that we have.